In this video, we're going to discuss switching loops and the spanning tree protocol, or STP. First, we'll discuss what switching loops are and why they're a problem. Then we'll discuss the infrastructure STP uses to stop switching loops. Finally, we'll see an example of STP in action. Let's start with a simple network setup. In this diagram, we have a couple of switches with endpoints connected. Of course, we already know that if a broadcast frame is sent from this workstation on switch A to the local switch port, switch A is going to copy that frame to all its other ports. The frame gets copied up to the station on the top, to the station on the bottom, and of course, to switch B next door. Switch B receives the broadcast frame, and it does the same thing. It copies the frame to all connected nodes. It doesn't matter which switch you're connected to, a broadcast frame will propagate to all the switches it can reach. This is normal behavior, and it's how things are supposed to work. But what do you think would happen if we added a second link between these two switches? You might be saying, hang on, why would I do that? Here's why. One link creates a single point of failure. But with two, if anything happens to the first link, you can use the second to get information between the switches. Let's look at how broadcast traffic is handled in this configuration. The workstation on switch A sends a broadcast frame to the local switch, and it's copied to all other ports, including the ports that lead to switch B. Switch B receives the frame, copies it to the workstations, and copies it to the other port on that switch, which lead back to switch A. That broadcast frame actually takes a loop here and ends up right back on the segment leading to switch A. The same thing would happen to the signal coming in from the bottom. It would loop back through switch B on the top link back to switch A. This is called a switching loop. It's a bad thing. Now, data is circling around the network as fast as the switches can process the frames. This is the beginning of what's called a broadcast storm, and it can take down your network very quickly. So how do we fix this problem? With the spanning tree protocol. This protocol assigns one bridge or switch for each route as the designated bridge. Only the designated bridge can forward packets. Redundant bridges and switches are assigned as backups. Having just one active bridge makes switching loops impossible. There's not a loop for them to travel anymore. STP also provides redundant paths between devices, enables dynamic role configuration, helps the network recover automatically from a topology change or device failure, and identifies the optimal path between any two network devices. These important functions are why it's configured and enabled by default on all Cisco devices. To really understand how STP works, you have to understand the infrastructure of priority mechanisms it uses to keep things running smoothly. It categorizes three things: bridge roles, port states, and port types. We're going to discuss each in detail, starting with bridge roles. The root bridge is the master or controlling bridge. There's only one root bridge in the network. You can establish a secondary root bridge that'll take over if the primary fails, but only one can function at a time. The root bridge is the logical center of the spanning tree topology in a switched network. STP uses the switch with the lowest bridge ID as the root. The bridge ID is composed of two parts, a bridge priority number and the MAC address assigned to the switch. The default priority number for all switches is 32,768. This means that for unconfigured switches, the switch with the lowest MAC address becomes the root bridge, but it's possible to manually configure the priority number and force a specific switch to become the root. The root bridge periodically broadcasts configuration messages that are used to select routes and reconfigure the roles of other bridges if necessary. All ports on a root bridge forward messages to the network. A designated bridge is any other device that participates in forwarding packets through the network. They're automatically selected through the exchange of bridge configuration packets. To prevent bridge loops, there's only one designated bridge per segment. All redundant devices are classified as backup bridges. Backup bridges listen to the network traffic and build the bridge database, and they don't forward packets. A backup bridge can take over if the root bridge or a designated bridge fails. The second prioritization mechanism STP uses is port states. Port states are the stages that special packets called Bridge Protocol Data Units, or BPDUs, must go through as they're exchanged between devices. Devices send BPDUs out all ports. BPDUs sent and received from other bridges are used to determine the bridge roles and port states, verify that neighbor devices are still functioning, and help the network recover from topology changes. During the negotiation process and normal operations, each switch port is in one of 5 states: disabled, blocking, listening, learning, or forwarding. A port in the disabled state is powered on, but doesn't participate in forwarding or listening to network messages. A bridge must be manually placed in the disabled state. When a device is first powered on, its ports are in the blocking state, and backup bridge ports are always in the blocking state. Ports in a blocking state receive packets and BPDUs sent to all bridges, but they don't process any other packets. The listening state is a transitory state between blocking and learning. The port remains in the listening state for a specific period of time. This time period allows network traffic to settle down after a change has occurred. For example, if a bridge goes down, all other bridges go to the listening state for a time while the bridges redefine their roles. A port in the learning state is receiving packets and building the bridge database, associating MAC addresses with ports. The root bridge and designated bridges are in the forwarding state. They can receive and forward packets. A port in the forwarding state can both learn and forward. All ports of the root switch are in the forwarding mode. The last priority mechanism SDP uses is port types. During the configuration process, ports on each switch are configured as one of 3 types: a root port, a designated port, or a blocking port. The port on the designated switch with the lowest port cost back to the root bridge is the root port. Each designated switch has a single root port, a single path back to the root bridge. Root ports are in the forwarding state. The root bridge does not have a root port. One port on each segment is the designated port. This port identifies which port on the segment is allowed to send and receive frames on that segment. All ports on the root bridge are designated ports unless the switch port loops back to a port on the same switch. Designated ports are selected based on the lowest path cost to get back to the root switch, like 10 megabits per second or 1 gigabit per second. If 2 switches have the same cost, the switch with the lowest priority becomes the designated switch, with the port on that switch being the designated port. If 2 ports have the same cost, the port on the switch with the lowest port ID becomes the designated port. The port ID is derived from 2 numbers, the port priority and the port number. The port priority ranges from 0 to 255, with a default of 128. The port number is the number of the port. For example, the port number for FA0/3 is 3. With the default port priority setting, the lowest port number becomes the designated port. Designated ports are used to send frames back to the root bridge, and designated ports are in the forwarding state. A blocking port is any port that's not a root or designated port. A blocking port is in a blocking state. All right. Now let's put all these elements together with an example of spanning tree protocol in action. Let's go back to our switches connected with the redundant links. Let's say switch A's bridge ID is 1 and switch B's is 2. These are not what bridge IDs actually look like. They're several bytes in length, but we're going to use 1 and 2 for simplicity. The spanning tree protocol sends BPDUs out each connected port when the switches come up. The BPDUs carry the bridge ID within them to alert the switch next door of what's connected to it. Switch B does the same thing and sends BPDUs out all connected ports to look for neighboring switches. Switch B is going to see BPDUs coming in from switch A over both these connections. Because switch A has a lower bridge ID, which represents a higher priority to the spanning tree, it'll have the first chance at taking responsibility for segments. There's only one way to block the loop in the middle. You have to sever one of the connections. One of the ports on switch A or switch B is going to have to be put into a blocked state to effectively sever the loop. Because switch A is the dominant switch in this case, it'll remain active on both its ports. These 2 ports will remain in a forwarding state on switch A. The connection with the lowest port number on switch B may be E0 or Ethernet 0. Let's say that it's the bottom port. This link will be active between the 2 switches, but on switch B, the other side of this top link will be in a blocked state. What you end up with is one connection between switch A and switch B, this bottom connection. No data is traversing the top connection between the two switches, which eliminates the loop. If the bottom link goes down sometime, this top link is still active. It's still physically connected to the two switches. Spanning tree would realize that there's no longer an active connection between the switches and unblock this port so that the top connection becomes active again. All right, let's review everything we've talked about. Without the spanning tree protocol, a switching loop could bring down the network very quickly in the case of a broadcast storm. So STP is configured and enabled on all Cisco devices. It uses prioritization mechanisms to eliminate switching loops by comparing switch metrics and determining which active ports should be blocked to prevent them.